So questions, what kind of topics would y'all like to review? Questions about, yeah, anything?
Could we discuss the Gauss-Bonnet theorem when we're triangulating a surface and the relationship between like interior angles and exterior angles and like how to consider those in the case where it's not a disk, for example?
Okay, so the good news, you don't really have to triangulate too many things. Really the only thing you would ever need to triangulate is if you're trying to figure out what the Euler characteristic is. And so in terms of applications of the Gauss-Bonnet theorem, right, just to write it down, right, Gauss-Bonnet, which is one of my favorite theorems. Arguably, Gauss-Bonnet is a special case of my favorite theorem, which I guess if I had to pick one might be the positive mass theorem. But the Gauss-Bonnet theorem is, and then this would be the positive mass theorem dimension 2 in a certain sense. But the Gauss-Bonnet theorem says that you have some surface with some topology, right, with some boundary. By the way, it could have multiple boundaries, right? Let's see here. Okay. And let's say there's some topology as well, right? We'll call this surface here M2. And then you can see that the boundary of M has two connected components, right? Then the integral over M of the Gauss curvature times the area formula, so then you integrate to get area, plus the integral over the boundary of M, both components, or all the components, of the geodesic curvature times ds, that this equals 2 pi times the Euler characteristic of M. And this is where the Euler characteristic of M is equal to faces minus edges plus vertices of any triangulation you might do, right? Now you might say, well, gosh, how would I triangulate that? It looks really hard to do, and it is really hard to do. So I probably don't recommend it, actually. Okay, but that's the definition. It's the f minus e plus v of any triangulation. But then that raises the question, oh, but then how do I know what the Euler characteristic of that is? Well, I know the Euler characteristic of this is equal to, well, it's 2 minus 2g, right? Where g is the number of holes, right? And the number of holes is 2, right? Because remember, for a sphere it's 2, and then for a donut, which is torus, it's 0. It goes down by 2 each time you add a donut hole, right? So there's 2 donut holes there. So this is going to be 2 minus 4, which is minus 2, right? And then therefore the Euler characteristic of this same thing, right? But now I remove 2 faces, right? It's just going to be Euler characteristic minus 2, and then subtract 2 more, and so I get minus 4. Okay, so that's how I would compute the Euler characteristic. It's just going to be a lot easier. Now, there's another thing to know, I suppose, and that is just in terms of useful identities, the Euler characteristic of the connect sum, right, of 2 surfaces is equal to the Euler characteristic of A plus the Euler characteristic of B minus 2, right? And by the way, do y'all see that the thing in question there was a connect sum of this with itself, wasn't it? I mean, not that you would ever do this problem this way. This is just like a weird test, right? But the other characteristic of this, if I filled it in, it would be 0. That's a torus, right? And then remove a face, so that's minus 1. And then minus 1 plus minus 1 equals minus 4. Right? I say it in the funny way, right? Because you have to subtract 2, right? So it's minus 1 plus minus 1 is minus 2, and then minus 2 is minus 4. And that's the answer we got before. Does that address the question you're talking about, or do you want to get more into the proof? Like maybe you had a different question. So you want to get more into the proof?
I understand the proof. There were just a few questions on the practice exams. I'm going to try and pull it up quickly. But one, basically, that described like a ball, and then it was, I don't know if it was triangulated, but like some of the faces were described as like hexagons or, yeah, these guys. It was
Remind me, yeah. Okay, fun problem, yeah.
Yeah, I like this. I did not understand in terms of like adjusting
Remember
for.
the problem. Me too, real quick. Oh, hyperbolic space here, right? No, sphere. The unit sphere.
It's question 2016 on or 2016 question 4. If anyone cares to pull it up on their own computer.
Okay. Okay, what year is it?
2016.
Number 4, what year?
Oh, sorry about that.
2016?
Question 2016 question 4. Sorry.
Final exam. Is this it?
Mm-hmm.
Okay. Now, on this problem, there's a pentagonal tiling of the sphere. So think of a sphere here, right? And then it's tiled by pentagons. Okay, so let's just try to. This is an art challenge for me to draw it. Okay, so I think I can do something. Okay, but just by analogy, by the way, y'all know that you can tile the plane by hexagons, right? And so on, right? This is a tiling of the two-dimensional plane R2, right? It turns out you can tile S2 with pentagons. And you might say, well, what's the best way to understand this? Well, there's something called a dodecahedron, right? And so the way you draw a dodecahedron, this is like art class here, right? Is first you draw a regular pentagon, which I didn't quite do. I could do a little better, I think. Okay, so try to draw a regular pentagon. Yeah, there's a. See, I was pretty far off there. Don't draw a hexagon. I don't know, still not quite, I'm not calling it good enough, I think. All right, so you draw a pentagon, and then you go out like this with shorter sides. And then you put in the pentagons here. And there you go. And that is a 12-sided dodecahedron, right? Because you can't. There's the other side you can't see, right?
Pretty good.
Yeah, thank you. Been practicing. There's also, by that way, an icosahedron that has 20 sides, and that can be drawn with practice as well. It takes a little bit more patience. Okay, now, can y'all imagine that you put this on the inside here and then you project it onto the sphere with a central light source at the origin, right? Just project it, right? Then each of these straight lines will be projected out to parts of great circles, right? And then what we'll get is a pentagonal tiling here. So let me draw 5 points. And these will be parts of circles, okay? And so the key point is that each of these has 120 degrees here, and then the geodesic curvature here is 0 on all 5 sides. Okay, and then imagine a pentagonal tiling of this, right? It just keeps on going. Right. I don't know. I won't bother to put in the rest of the picture, right? But I just drew the one side, right? It's a projection out of the platonic solid here called the dodecahedron. Fair enough? And by the way, why do these have 0 geodesic curvature? Well, remember we're projecting from the very center of the sphere, right? And so take any line, and then take the center of the sphere, right? The origin, right? Take any line that defines a plane, right? A point and a line, as long as the point doesn't go through the line, right? That defines a plane. And that plane is a plane that goes through the origin. Any plane that goes through the origin is a plane of symmetry of the unit sphere, right? And so where it intersects is going to have 0 geodesic curvature because is it curving to the left or to the right? Well, it's got to be doing both the same by symmetry. Okay. So. And then these have to be 120 degree angles. Why? Because they're all the same angle and it adds up to 360, right? So then I think what the problem is asking you to do, there's an extended version of the Gauss-Bonnet theorem I don't usually write down, which is you can add in, what if you have corners, right? So this is, we're assuming the boundary doesn't have any corners, right? But what if you do have corners, right? Well, the key thing to remember is that, the way corners, the way you handle corners is that if you take the integral over the geodesic curvature ds over a corner, this is equal to delta theta in radians. Now, why is that? It's because, remember, geodesic curvature is theta prime of s ds, right? And so it's sort of like a distributional, change in the angle, right? Because it's curving, at a corner, it's curving very, very rapidly. And so the curvature is sort of like a Dirac delta. But the point is you're integrating theta prime of s ds, so by the fundamental theorem of calculus, it's delta theta. It's the change in theta. Okay, so all you do in terms of remembering I don't usually write it down, but then I could, if I wanted to, I could say minus the corners here, because it doesn't really technically make sense to do this, and then I could say plus the summation over the corners of delta theta. Okay? I could say, let's say the corners are parametrized by k, and then delta theta is okay, whatever. So that now we have the Gauss-Bonnet theorem with corners. Okay? And it's only fair. I said don't integrate over the corners, right? So I'm just telling you how to integrate over the corners. Right? It's the corners count this way, right? And that's in the book. And if you follow our proofs through carefully, that's what you get. Okay, and so then if we then apply the Gauss-Bonnet theorem to this, this is a sphere of radius 1, so this is the unit sphere here. And the question is, hey, what is the area of each of these pentagons? Right. So let's call the area of each of these pentagons A. Okay. Then when we apply this theorem, well, you're telling me it's the unit sphere, so k equals 1, and then so it's 1 times dA. dA is the thing you integrate to get the area, right? So if I do this, just integrate over one pentagon, I'll get the area there, right? So I get A plus, and then we have the integral over the boundary. Well, these are all geodesic boundaries, so that's geodesic curvature is 0. And then you got to add in the contribution from the corners. And so you see there's 5 of them, each 120 degrees. Otherwise, 120 degrees is 360 over 3, right? So that's going to be 2 pi over 3, and we do it in radians. And then times 5, right? Because there are 5 corners, pentagon, right? And then we know that this is equal to 2 pi times the Euler characteristic of a disk, which is 1. So this is what we get when we apply the Gauss-Bonnet theorem with corners to that pentagon on the sphere. Does that make sense to everybody? Any questions about that?
Can you re-explain the 2 pi over 3?
Sure. So first of all, that's 120 degrees, and that's 120 degrees, but the theorem is you have to do it in radians. Right? So it's 120 degrees times 5, and that's just plug into the formula that, oh, wait a second. I didn't do that right, did I? 120 degrees is the internal angle, but how much did you turn is it's 60 degrees. So I think you caught a mistake. Okay, so the amount you turn, sorry, it's how much, this is how much you turn. So these are exterior angles, right? So well, let's see here. If we go like this, it's how much you turn, right? And then we know that that's 60 degrees, which is 1/6 of 360, right? Does that make sense to everybody? Anybody see any other mistakes I made? I wasn't going to get the right answer here. Yeah. Other question, comment?
I think you missed the Gaussian curvature.
What's that?
You missed the Gaussian.
Oh yeah. Oh no. The Gaussian curvature is 1, so it's 1 times dA, right?
Okay.
And so that's why we get the area here, right?
Mhm.
By the way, had this been on hyperbolic space, the Gauss curvature would have been -1, right? So you can tile hyperbolic space by heptagons. These are 7-sided. So 6-sided, it gives you the plane. 5-sided gives you a sphere, and then 7-sided gives you hyperbolic space. Heptagons, I think it's called. And so that's why we have a +1 here, not -1. Now let's see if this actually works, because we actually know the answer, by the way. We know that there are 12 sides on this, right? and in some sense, we're going to be proving that because what we're going to find is that this is exactly 1/12 the area of a whole sphere, right? Because there's 12 sides, and so of course it's going to be 1/12, right? But that's using knowledge outside the problem, which is that this dodecahedron exists, right? So let's see if we get 1/12 the area of a sphere. So this is going to be pi over 3. So we have so the area then is equal to 2 pi minus 5. Is it 5 pi over 3? Which equals 6 pi over 3 minus 5 pi over 3, which equals pi over 3. Now, does that check out? The area of a sphere is 4 pi r squared. R is 1. So the whole sphere is 4 pi. You divide that by 12, you get pi over 3. So that does check out. Thank you for finding my mistake before it wouldn't have worked otherwise, right? If I get this angle. Thank you. Other questions or comments? Yeah, hyperbolic space can be tiled by the way, by heptagons. Talk about that a little bit. Why are we using a 5-sided thing here? Well, I mean, why not tile with hexagons or something? If you try to do it with hexagons, then you'd still have a 60. Again, suppose we have the same connectivity where we have 3 things coming together, right? At a point. Then notice that it ended up wouldn't be possible because what you would get is let's see, you have 60 degrees still here, so this would not change, but that 5 would become a 6, right? That's the only thing that would change if you tried to tile with hexagons. And if that 5 becomes a 6, then that's 2 pi is 2 pi, the area is 0. And you're like, well, I guess you could. You could sort of tile it if you had infinitely tiny little hexagons, right? They would sort of tile a tiny little part, right? But ultimately, it's not going to work, right? So you're not going to get something that actually tiles, right? Just right on the edge of what would be possible. It turns out it's not possible. The area was 0, which doesn't make any sense, right? And now on this other hand, suppose we are in hyperbolic space. Now, how do you draw hyperbolic space? It's hard to do, but let's say we have. We'll call this the Poincare disk. That's the conformal representation of hyperbolic space. Which way does the accent go? There's an accent here somewhere. Does anybody remember? E is a normal one, like this, or backwards?
Forwards, regular.
Like that?
Yeah, that's right.
Okay. Never. Again, at least I knew there was an accent. Okay. All right. And, okay, so now Poincare disk, I'll remind you that geodesics, this is infinitely big, right? If this is the origin of there is no origin to the Poincare disk in the same way there's no origin to the surface of a sphere, okay? So I'm taking the center point of this particular projection of the hyperbolic space, okay? But every point is the same, in fact, just like every point on the sphere is the same. But then the point is geodesics are just straight lines through the origin. Excuse me, it's not the origin. Through the point that's centered, it's the coordinate origin, I guess you could say. And they're also circles that meet perpendicularly at infinity. Meet the boundary perpendicular. Okay, now all those curves I just drew are infinitely long. Because I'll remind you that the metric here is dx. It's the usual dot product, which I'll write as dx squared plus dy squared. And then if I don't multiply or divide by anything, that's just the usual metric on R2. But then you divide it by 1 minus r squared, and I think actually, don't you put a 4 here also or something like that? And then I think that's right. Something like that. Someone can tell me if I think that's right. So if I messed up, you just let me know. But that 4 is just a scaling, but it's going to change the curvature. But anyway, this gives me a hyperbolic space with Gauss curvature equal to -1. What the hyperbolic space is the space of constant negative curvature. Now what's interesting is that it's really sort of to be in this, it's like the opposite of the sphere of radius 1, which has curvature +1, right? So this is your negatively curved space. That's homogeneous, every point is the same. This is your positively curved space, every point is the same. By the way, if you make a sphere bigger, the curvature goes down. Why? Because the Gauss curvature is 1 over r squared. Y'all remember that, right? It's the product of the min and the maxes, right? So one thing that's interesting, you should remember that curvature as units of units 1 over distance squared. So if you make it bigger, the curvature, if you make the metric 10 times as big, the curvature gets divided by 100. Does that make sense? It gets divided by 100. Doesn't mean it gets smaller, because if it's negative, it makes it actually bigger, right? Anyway, it gets divided by distance squared. Okay, it's 1 over distance squared. So if for example, yeah, you could scale this as well, right? Then, and by the way, you should know that the metric here, which is commonly called g, that has units of distance squared. So the metric is distance squared. Why? Because it's a vector dot product itself, which is the length of the vector squared, right? So metrics are distance squared, and then Gauss curvatures are 1 over distance squared. Geodesic curvatures, by the way, are 1 over distance. So here, let's just do units real quick. Dimensional analysis is kind of useful. 1 over distance squared. Okay, so I'll say 1 over distance squared. Now dA, that's area, that's distance squared, right? And so that's unitless when you put it together. Scale invariant. Geodesic curvature is 1 over distance times ds, which is distance, right? So that's unitless as well. And of course, another characteristic is unitless. All right. So if you're trying to do this in a hyperbolic space, then let's say you do exactly the same problem, and we're gonna tile with some regular n-gon, right? Let's say we try to tile with pentagons, right? So imagine I draw a pentagon here. I'm trying to tile with pentagons or something like that, right? Well, then the point is we do exactly the same computation. The difference is that the only thing that changes is there's going to be a minus sign there, right? So let's say that let's try to do it with n-gons. How about that? 1, 2, 3, 4, 5, 6, 7. Let's say this thing has, and then we tile, and we'll say there's three at every junction, okay? Just like we had before. So 1, 2, 3, 4, 5, 6, 7, okay? And then repeat dot 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 dot. Okay, and let's say it's an n-gon, okay? So we do the computation there, then what we're going to have is the Gauss curvature is -1, so we get -1 times whatever the area of this thing is, right? Call it A. So we get minus A, right? In fact, let me just call it -1 times A. It's probably -1 times A. And then plus, well, again, we're trying to tile with geodesic edges, right? So this is supposed to be 0. But then we have the corners, right? And how much are you turning at each point? Well, you're turning pi over 3. That's 60 degrees, right? So we're still assuming that we have 120 degrees, and you're therefore turning 60 degrees, right? So that's pi over 3 times the number of sides in your n-gon, right? And then this equals 2 pi times the Euler curvature of the disk, which is 1, so we get 2 pi times 1, right? And so then what does this tell us? It tells us that A equals, so now here we have to put A on the other side, right? And so let's put that 2 pi over there, which by the way is, that's 6 pi over 3, right? So I can put a 3 here, and I can factor a pi out. And then what I have here is n minus 6. Okay? So if I want to tile hyperbolic space by n-gons, that's the area of each side. Now you'll notice that this makes sense as long as n is 7 or bigger. If n equals 6, we're trying to tile with hexagons. And we kind of knew that wasn't going to work. That's how you tile flat space, right? But if you go up to 7, that would be the first case this makes sense, right? Yes?
Wait, why is it pi over 3?
That's just this right here. That's the turning angle because you turn 60 degrees, which is pi over 3.
But you turn 60 degrees regardless of how many.
Yeah, each time you get to a corner, you turn 60 degrees because it's going to be at each juncture it's 120, 120, 120, and so therefore you're turning 60 degrees. Yeah. So that delta theta here. Another way to is how much you're turning. Another way to write this, by the way, is the amount you're turning. It's pi minus the interior angle, theta sub I. Okay. I think they call it theta sub I for interior angle, right? So if you have 120 degrees there, 180 minus 120 is 60. Otherwise known as pi over 3.
Wouldn't 60 degrees be pi over 6?
That's 30 degrees. So pi is 180 degrees.
Pi. Oh, I get
Yeah, it's 2 pi over 6. Yep. Yep. Very good. Okay, other questions?
Maybe I missed when you were talking about this, but the other characteristic of a sphere is 2, correct?
Correct.
So why is this 2 pi times 1?
Oh, because the only characteristic of a disk is 1.
Oh, it's a disk.
Right, we're applying the Gauss-Bonnet theorem just to this pentagon here, or otherwise known as a disk topologically. Yeah. Question.
The G you wrote down there seemed to have units of distance -2.
Here?
Yeah.
Oh, I get what you're saying. Yep, it does. Because you're thinking, okay, distance squared divided by, well, if you think of this as distance squared, right? Then this would be distance to the fourth, and so you get 1 over distance squared. That's the argument you're doing. In this construction, this factor here is unitless.
Okay.
So really, I could say r divided by distance squared or something like that.
Yeah.
Okay. A good question.
Yeah, the one's clearly meaningless.
Yeah, yeah. So to make for this to technically make sense, this r is to be interpreted to be unitless. Good question. I mean, another way to understand this, by the way. I mean, the metric is just always distance squared because it's a vector dot product itself. So it's the length. It's the length squared of a vector. It's units. Well, it has to be other for it to make sense. Yeah.
So can I, like, when you say disc, is it like does it look like a contact lens? Like, is there like a protrusion upward, or is it just flat? Because that, to me, seems like it has.
This.
Yeah.
It's just a round sphere. It's a perfectly round sphere
Sure.
being tiled by 12. I'm going to call them pentagons. Okay, they're subsets of our perfectly round sphere. They have 0 geodesic curvature boundaries and 120 degrees at each of the 5 angles, and they tile. So they're subsets of a sphere. They bulge in that sense, but really they're just tile the sphere.
Okay.
Yeah.
So then, at what point does like a disc become like half a sphere, and then
I mean,
guess
there's
it
two
would
different
then-
senses. There's the metric sense and there's the topological sense. So sometimes when I say it's a disk, what I mean is topologically a disk, meaning that forget the rigid structure, right? Like the other characteristic of a disk, no matter what its geometric shape, it's always 1. So for example, half a sphere is a disk, topologically.
Okay.
Yeah.
So the exterior angle is independent of like whatever polygon you choose, right?
The what?
The exterior angle that you're choosing.
Yeah, in this construction, I was saying let's tile so that it's always 3 coming together at a point, which means they're all 120 degrees, right? So you're always turning 60 degrees for both of these problems. So that's part of the problem. Yeah, given to you.
So that means the interior angle of like any polygon and like that's like tiled is always going to be 120 degrees.
If all 3 angles are equal, it has to be 120 degrees, right? Because it's 360 over 3. Yeah. 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 By the way, we could have done the same computation. What this is showing is a hyperbolic space. Turns out it's. By the way, it shows that if it can be tiled, then here's the area. So you can see the n would have to be at least 7, right? But did we actually prove that hyperbolic space can be tiled by a heptagon or an octagon? Did we actually prove that? You still need to demonstrate that. Like, does such an object exist? Blah blah blah. There's some more discussion. The answer is yes. It turns out, right? So you can choose any n greater than or equal to 7, and you can tile hyperbolic space. Now, if n equals 6, we know we can tile R2. And by the way, if n is anything 5 or less, like 5, 4, or 3, right? So in other words, you can tile the sphere with something with 5 sides. That comes from the dodecahedron. You can also do something with 4 sides. That's called the cube, isn't it? So I do exactly the same thing, right? And I can blow this out, right? And I can tile with squares, 4-sided regular polygons. And you can also do it with a tetrahedron. Let's see here. Which, by the way, is triangle. So this will be n equal 3, n equal 4, n equal 5, and you can do it with all those. Now, how about n equal 2? Well, this doesn't even make sense, right? And by the way, the formula you get up here is just exactly the same calculation, except instead of a, it's minus a, right? So it would be 6 minus n. And if n equals 2, then you get 6 minus 2 is 4 pi over. You actually get an answer, right? Except that what is a two-sided polygon? Doesn't make any sense. There's no such thing as a two-sided polygon, right? So so n has to be 3, 4, or 5 when you're tiling the sphere. You can do it with triangles, you can do it with squares, you can do it with pentagons. That's it. I mean, what is a two-sided regular gon? I mean, it would just be, the side comes over like this and it comes back, right? I mean, I guess but it doesn't have any area, right? So how could you give it positive area? It doesn't make any sense, right?
But on a sphere, you can have that. You could have two geodesics that intersect.
That's a good point.
It just has to be 1/3.
Oh, actually, you're right. So it is, actually, no, it is, you're right. There is an answer.
Oh, yeah, it's the
Oh,
one
there is an
side.
answer. Oh, you're absolutely right. Thank you. You guys corrected me. You caught me. Oh, this would be a good test question, not for your year, obviously. Yeah, what you're showing is that you can just, let's see, what area do we get when n equals, so up here, for the sphere, the area is going to equal pi 6 minus n over 3, I think, right?
Like a beach ball looking thing. That was technically a tessellation of the sphere.
So if n is 2, 4 pi over 3,
But it's like
that means there'll be 3 of them. Yeah, okay, yeah, so you just go up to North Pole. Yeah, just let's let this be the North Pole, right? So one like this, one like this, one like that, right? Okay, yeah. So if you look at it from the side, right? I don't know, but let's see here.
a beach ball.
So you just have 120, make that 120 degrees, right? There's just going to be like a lunar slice, right? Whatever you want to call it, right? So this thing here, right? A third of a sphere. You guys get what I'm trying to draw? From the top down, it's just chop it like that, right? So you get these lunar slices, right? And and they're all meeting at 120, 120, 120, right? So the formula went beyond my intuition. I couldn't quite visualize it, right? How can you have a two-sided regular n-gon, right? Well, you can on a sphere. Thank you. You got that, right? Very nice. Very nice. So yeah, this formula gives you the right answer, even though I couldn't visualize it, with a regular two-gon, right? These are regular two-gons, right? On the sphere. They don't exist in the plane. And by the way, they don't exist in hyperbolic space either.
Yeah.
Because in hyperbolic space, see, what's interesting is if you're in a plane and a geodesic one starts out this way and one starts out that way, they just continue to get further apart, right? If you're in hyperbolic space, same is true, but they get even further apart, even more further apart. But on a sphere, they can curve back together, right? They can start out going away from each other, and then next thing you know, they curve back together and intersect. So that's the unique property about the sphere that we're using here, is that these are still geodesic sides, and they were going away from each other, and then they curved back together, as if there was like gravity pulling them together, which there was, because it was positive curvature. Positive curvature is like positive mass, and positive mass is like gravity, right? So this is actually behind gravity. Gravity pulled them together. And so yeah, so n equal 2. Now I'm going to go out on a limb and say n equal 1 doesn't make any sense.
It's just 1 line.
How could it? It probably does actually, because you can just come back to yourself. Oh gosh, does that make any sense when n equals 1?
Because the change in angle would be 0, so it's just a equals 2 pi times 1. And then you add both of those halves together, it's 4 pi.
It's the equator.
For one thing is you get 5 pi over 3, and that doesn't divide into 4 pi, so I'm going to say that n equal 1 doesn't make
It
any
wouldn't be
sense.
pi over 3 anymore.
Well, yeah, you can't just. There's no reasonable way you could say that 3 of them meet because they don't have vertices anymore. Just means itself.
Yeah, so n equal 1 doesn't make any sense. I really don't think it does, right? Am I right?
Yeah, I mean it doesn't have vertices, so you can't have big junctions between bases.
Or maybe you could connect up to yourself is the thing I was thinking, right? But the
Yeah.
problem is the angle will always be 180 degrees. And so you're not going to get 3 at an angle. Now, if you were allowed 2 at an angle, then technically you've got something, right?
I mean, like you can just divide a sphere in half with a great circle.
Yeah,
It's
yeah.
like
So you could do that. It doesn't fit into our pattern because we were requiring it to be 3 at an angle, right?
Yeah.
But if you were to compromise on that, then yeah, then you can have a one-sided n-gon. It's just it goes from the North Pole all the way around to itself. So one side. So I guess you can.
Encapsulates the sphere in that it just divides it
Yeah.
in half.
Yeah, so I would say that does seem like a one-sided n-gon, a one-gon exists on the sphere, and it's just half a sphere, I guess, right? But it doesn't quite fit the requirements of having 3 n-gons coming together at a point. So I'm going to say it breaks the pattern. Okay, so that's a good example of how just because you have a formula that says that you get an answer for something, it doesn't mean that something exists, right? Okay, so we say n equal 1 doesn't actually exist, even though we get an answer for it in this formula here. Okay, other questions, comments, observations?
I have another question.
By the way, you can Google this stuff. If you want to see a heptagonal tiling of the hyperbolic face, just Google it. It's actually, I love stuff like that. It's actually awesome. And M.C. Escher, by the way, was kind of an artist you may have heard of who took advantage of the beauty of tilings of hyperbolic space and turned it into artwork. So, you may appreciate some of his artwork. It's got this mathematics behind it. Yeah, other questions, comments?
This is probably a really fast one. I think I'm just overthinking it. But like compactness of a surface, like if a surface is compact, one of the problems it says it's closed and bounded, but like, what does it mean to be?
Okay, vocab.
Yeah,
Vocab.
It's kind of a vocab.
Okay, I'm trying to remember what the definition of what. It's actually, I haven't scrutinized the definitions of things really well. I think a closed, okay, what's the definition? A closed surface is one that's compact and does not have a boundary. Is that the definition? I think so, right?
Closed surface doesn't have a boundary.
Yeah.
Yes, I think
That's
a
true.
closed surface is a compact surface with no boundary. All right, now, what does it mean to have no boundary? Well, you know it means to have no boundary, right? Okay. What does it mean to be compact? It means that you contain all your limit points. Okay, so excuse me, that's what it means to be closed. Sorry, the compact means that every sequence has a limit point. Sorry. Right. So, for example, R2 is not compact because if I just look at a sequence of points going off to infinity, right? Well, there's a sequence of points, but it doesn't converge into anything. But if you look at, for example, a closed disk, let's just take the set of points. And I could say then the complex plane, right, and say the norma is less than or equal to 1, right? Then any sequence of points you can imagine has a limit point, actually. There's no way for it to not accumulate somewhere. And there's a proof that if what's compact and what's not compact, and this is like point set topology class. I encourage you to take a point set topology class. Anything that, for the purposes of this class, all you need to know is that a closed surface is one which is, we'll define it as no boundary and finite. Okay, so in other words, we're not allowing an equatorial boundary, like the half a sphere has a boundary, right? So we're not allowing for that. And then, or else we're not allowing like something that goes off to infinity, like the plane.
Okay. All right.
Okay. Yeah, I mean, learn point set topology sometimes. It's actually pretty easy. It's a bunch of definitions. Rather than me telling you all the definitions of point set topology, because it is like a course in and of itself, right? I mean, it's a couple of weeks. Let me tell you something. Let me give you an example of a topology, rather than telling you what a topology is. Fair enough? This will not be on the final. But there's a funny story here I want to share with you. At least, it's a funny story. Now, is it a true story? I suspect it's based on truth. Based on a true story. Because what topology is about is trying to make sense of this idea of what if we look at surfaces, but we don't care about the rigid structure. We just want to know how they're connected, right? So in other words, you guys have heard that the surface of a coffee mug is equivalent to the surface of a donut, right? Because you have one sort of handle on in both cases, right? So you can morph one into the other. It's saying like take a beach ball that's not inflated, and then all the different spheres you can make of that beach ball are all the same, right? We're saying topologically a sphere. We don't care about the actual rigid structure. And so then what you do is, let's say you're trying to understand the topology of, for example, R2, right? And then what it comes down to is talking about what your open sets are. Okay. So R2 is, you could say it's R2. What is it equal to? Well, it's the union of all these points x comma y, right? Where x is a real number and y is a real number, right? So you start with what is R2? Well, that's what R2 is, right? But how are these points all connected, right? Well, you have to define what your open sets are. And so what you do is you say, okay, well, how about we define, this is your R2 here, right? Given a point P, look at any ball of radius epsilon around P. And so this ball of radius epsilon around the point P, this is equal to the set of points Q such that the distance between P and Q is less than epsilon, right? And so we could find that to be an open set, right? And then we have some rules for it to be a topology. I think there's 3 rules. Gosh, one is, let's see here. Boy, this is really testing my memory here. Okay, this is also slightly embarrassing if I can't get this right. Okay, so I think the empty set and also the whole surface, everything. In this case, it's R2 are open sets. How do you draw the empty set? Is that like a 0 with a line through? Is that the empty set?
Yeah.
Okay, are open sets. I think.
Yeah.
Okay, and then you talk about the union of open sets and the intersection of open sets should be open sets.
Yeah.
Right? Now this one's a little subtle, okay, because it's the infinite union, union of open sets are open sets, right? But then the finite intersections, right? Finite intersections. Of open sets are open sets. Now, where these rules come from? Well, it's just based on this example in R2. We're using these balls, right? And you'll notice that if I take any finite union, that should probably be an open set too. If I take any finite intersection, but there's this thing that you can't take infinite intersections, because imagine I take the intersection of this ball with this ball with this ball with this ball, and I do it infinitely. What I'd only have left is the single point at the end, right? And that open set doesn't have any neighborhood around it, right? And we don't want that to be an open set. And so one of the key properties of an open set is that what we like is that if you're given an open set, given any point, open set is like a set that doesn't contain its boundary. Is the way I think of it, because given any point in the set, there should be another open set around it, which is completely inside the open set. Right? So the idea of an open set is that for every point inside of it, there exists a neighborhood around that point. Okay? And if you have these assumptions, you can prove that, I think. All right. I forget. I think that ends up being an exercise. Is that an exercise or a definition of open set? I think that's something you end up proving from these definitions. Because what you want to do is you start with this example of what an open set is, and then you come up with a definition that says, you know what, whenever you have a certain number of properties, I'm not positive, I think these are most of them, not all of them, then we call this a topology. Okay, we call this a topology for your space, for your set, a topology for R2. So in other words, we have our standard topology for R2, but actually you could put other topologies in R2 as well. Okay, and it's going to give you something completely different. All right, so there's not actually just one topology you could put on R2. So for example, one thing you could do with take the standard topology on R2 and add a point at infinity. This is done, people talk about that all the time. You've probably heard of people say add a point at infinity. And y'all may recall that there's stereographic projection, which we did in this class, right? You can take a sphere, stereographically project it to a plane. Now, technically, you have to remove the North Pole, right? Then you stereographic project an S2 onto an R2. Well, given an R2, you can get that sphere back if you can project to the sphere, but now you're missing that point at the North Pole, right? So you have to add that point in. But not only do you have to add that point in, you got to modify the topology too, because you have to. So when someone says add a point at infinity to R2, what they mean is add the North Pole back in, but also put in the open sets that contain the North Pole into the topology. Because we want to get an S2 back, right? And so how you do that affects what you get, right? And so typically people mean add in open sets such that you'll have an S2. Unless they don't mean that, they might mean, by the way, add in a circle of points at infinity, in which case you get a disk, right? Because R2 is also topologically equivalent to the interior of a unit disk, right? And then you could add a circle of points at infinity, right? So there's multiple ways to add in points at infinity, and it all comes down to what topology are you using, okay? Now here's the funny story that I'll share with you. And that is based on a true story. So it's the way the story was told to me. And the people who were telling me the story did their PhDs at Princeton. This supposedly happened at Princeton, and so it was kind of a story passed down from word of mouth from the people who knew the people who were there. So I think it's probably got some validity to it. But there was this grad student at Princeton. His name was Hausdorff. Okay, and the question came up in class, and basically the question is: if you have a point, right? And think about you have a point in R2 and another point in R2. But imagine it's not R2. Imagine it's just some something that's locally R2. So I think they were more or less assuming it's a topology, but not only that, they wanted to assume that locally around each point it's like Rn. Okay, so they were making additional assumptions beyond these assumptions. That's like locally like Rn. And the question is it possible to always choose an open set around this point and an open set around that point, such that the open sets never intersect? Right? Now, obviously, it's true in R2. Given you 2 points in R2, you can draw a sufficiently small disk around this point, a ball around this point, and a sufficiently small ball around this point so they don't intersect. And we just got through saying that we were choosing the topology so that it's locally like R2 or like Rn, more generally. And so any fool can see, right, that given 2 points in such a topological space that you should be able to do this property, right? And people were using this property to prove things, right? And then Hausdorff was like in the audience, is like, excuse me, how do you prove that you can always choose open sets that satisfy that property, that they don't intersect? And then the professor explained it to him, and the student said like, oh, I still don't understand. And like the professor tried to explain it to him some more, and then the student asked some more questions, and then as the story goes, this is where I don't know if it's true or not. Maybe it was another professor later on. It's like, okay, let me take a stab at this. Let me see if I can explain it to you, right? And the student just kept on saying, I don't see how that proves the argument. And then he gave a counterexample to their claim. It's not true, right? And so here's the counterexample, so you understand what's interesting about topology, right? Is that you can take the real number line. Turns out this statement is not even true in R1. It's not even true in a one-dimensional number line. And so what you can do is take the real number line. You guys understand what that is. There's your origin right there. Simple, right? This has a topology. What are the topology? Well, all the open sets are the usual open sets. Okay? But then what I want to do is I want to draw it differently. Okay? I want to draw this number line to where you take the origin and take all the positive numbers and just push them up a little bit, okay? And take the origin with you, okay? So there's a missing point here, right? Now, what are the open sets? I haven't changed the open sets. This is still an open set, right? It goes from negative A to positive B, right? That's still an open set, right? So I've represented them differently, but the open sets are exactly what they were before. And now what we want to do is you want to take this thing on top here and just double it and also draw it down here. Add in some new points. It's the non-negative numbers. Now what I want to do is I want to scooch this up, and then I want this to be an open set as well. You guys get the idea? So I want take the topology on this. This is the real numbers, right? Take that topology, look at all those open sets. Look at all the open sets on this real number line. And then take the union of all those open sets, right? And I want those to be all the open sets. Okay? And then of course, then I want intersections, finite intersections, add that into your topology. So I've given you a basis for which you can generate a topology. And it turns out that if you call this point here P and this point here Q, notice that any open set around Q and any open set around P, in fact, will intersect. They'll contain points over here in the negative real numbers. Right? And it turns out, but then on the other hand, locally, pick any point, it's like R1. Right? And so this is the counterexample that the grad student Hausdorff showed. And so from now on, everyone had to say, okay, you win. Let's assume this never happens. Let's never speak of this again. Okay, we'll just say that every space we want to deal with is, we'll call it a Hausdorff space. Okay, so that's where the term Hausdorff space comes from. It's from a student who would not accept an erroneous argument. Okay, so you got to keep your professors honest. And if you, every once in a while, you'll get your name on something, right? I guess the professors were at least nice enough to credit the student by naming this observation after Hausdorff, a very nice observation. And so now we just assume, usually, being human beings, we don't like to deal with complexity, and so we're like, okay, well, this seems ridiculous, right? You know, of course you should be able to have this property, so we'll say, from now on, let's just all have an agreement, let's only talk about Hausdorff spaces. Seems a little silly, doesn't it, right? Or I actually think we ignore Hausdorff spaces a little bit too much, and of course people do write papers on the non-Hausdorff papers, but generally no, yes?
If this is all one, how are the top line and the bottom line distinct?
Because when I say duplicate, what I mean is, let me be more precise. Let this be the negative real numbers. Let this be the positive real numbers. Let this be a separate copy of the positive real numbers. And then if I look at these two together, there's a natural topology, right? Take all those open sets, put it in. So your topology is a collection of open sets, right? So take all the open sets on this. If you put these together, you can think of it as the real number line, right? Take all those open sets, put them in your topology. If I scooch this down, take all these open sets and put them in your topology. And then use that to generate your topology. All right, so that's going to be mostly it, but also make sure I put all the unions of those sets in there and put all the finite intersections of those sets in your topology. Use that to generate your topology. And if you do that, then you don't have this property. Right? There exists 2 points, exactly 2 points in fact, P and Q, such that open sets around P and Q, they must in fact intersect. Like you take so in other words, just sort of figuratively, you have a point P and a point Q, and there's any open set around P has to intersect any open set around Q. There's no way for them not to intersect. And that's the explicit. Does that make more sense? Explain a little better?
So it's just by duplicating the positive number line, like none of the rules for topology have been violated. So
Yeah, there's work to check that I haven't verified. We have to make sure that we can use these sets to generate a topology, but you can. Yeah. And so, incidentally, what this is, I actually think this is interesting because, like for example, when we do general relativity, we always assume that your space-time manifold is a Hausdorff manifold. Like before you even start putting a metric on, we'll say, okay, suppose it's some sort of manifold, but what's a manifold? And if you start checking the details of what's a manifold, the Hausdorff assumption's in there somewhere. All right, so we're always assuming Hausdorffness. Okay, we're like, I don't want to think about it. Sort of like saying I don't want to think about a negative sign in the rule of Pythagoras. Right? Sort of like Riemann did, where he said, let's just make sure that the dot product of a vector with itself is always greater than or equal to 0. Right? Okay. Sort of like when people didn't want to consider the case where spaces might be curved, right? Oh, that sounds complicated. Let's not do that. It's a bad idea. Let's just all agree to stay on flat spaces, right? So I actually do think studying non-Hausdorff spacetimes is something that somebody needs to do at some point. Someone who has the guts, right? I mean, prove or disprove, is the universe Hausdorff? Right, because when you get right down to it, it's not, I mean, we say what the universe is, well, we say, someone would say, today they would say, well, a general relativity person would say, oh, it's, well, they'd probably say space-time, and then someone would say, well, what's a space-time? They'd say, well, it's a manifold equipped with a metric, as, you know, it's of signature 3,1, right? 3 space dimensions, 1 time dimension. And then someone would say, okay, I understand the metric stuff, that's what we've been talking about here, but what is a manifold exactly? Like, and then you say, well, it's like a topological space satisfying various properties. Okay, what properties are you assuming? One of them is Hausdorff. Another one is second countable. All right, I won't get into that, but it has to do with how many, it has to do with this collection of open sets. And I think it's assuming that you have a countable number of open sets that can generate the entire topology. Okay, and then so you get, so there's a countable number, like you can see in R2. See R2, if you just look at the rational centers with rational radii, that's all countable. Okay, it's a countable number of open sets, and then you can look at unions and intersections of all those and generate all open sets in R2. And they're like, okay, we like the fact that there's a countable number of open sets that can be used to generate all open sets. But that's just an arbitrary assumption. What if, so that's the second countability assumption. So someone who has the guts should study that. What if the universe, the manifold, which is the universe, what if this topology isn't second countable? Like, what does that mean in terms of physics, right? Because there's the key point. The key point is every time you make an assumption, you need to justify the assumption, right? How did we get from special relativity to general relativity? Did we add assumptions, or did we, in fact, what we actually did is we removed the assumption that the space-time was flat. Okay, I think that's very important to understand, is that general relativity is more natural than special relativity. Right? It's removing the assumption that the space-time is flat. Why should it be flat?
Special relativity is the special case.
Yeah, now we understand. Special relativity is just a special case, right? But assuming a manifold is Hausdorff is a special case too, right? And assuming a second countable is a special case, yes. Now maybe is the universe Hausdorff and second countable? Maybe it is. Maybe these are good assumptions, or maybe they're they're unjustified assumptions. Yes.
All metric spaces are Hausdorff. So how could you have a universe that's not Hausdorff if you're still like doing all this stuff with metrics?
I can see an argument for like a non-Hausdorff space-time for like using quantum collapse. Like if things are like non-deterministic.
Here's, you guys have such great questions, such a good discussion. The way I would interpret this picture, let's turn it this way. You guys mind if we rotate it? And so there's your one-dimensional negative numbers, right? And then what you have are, do you guys mind if I draw it sort of up? I'm going to try to draw it provocatively, right? So you get the point, there's a gap here, the point here, the point here.
But yeah, I mean that looks like a random event.
Imagine this, okay, imagine time splits. It's like a splitting. Like if you have a splitting of time, isn't that basically the multiverse?
Yeah.
Right, now take a cross product with R3. Take that art picture, cross product with R3, right? And the point is that at any point, if you're here, right, you look at your past, you just see this plus this branch. You don't see this, right? So at any point when you look backwards, you would just see R cross R3. You would say, I don't see the Hausdorff. So this Hausdorff just could be hidden in that way. So sort of these time branchings could be what sometimes people refer to as the multiverse, which by the way is not just in the MCU. It's also a serious physics theory, right? Whenever you do a measurement on a particle, right, and it's in a superposition of states, spin up, spin down, you measure it. Oh, look, it's spin down. You measure it a different time. Oh, look, it's spin up, right? It's possible every time you take a measurement, in one universe it was spin up, and in the other universe it was spin down, right? In which case, quantum mechanics becomes deterministic, right? It's just that in fact, we are over there experiencing it the other way as well. Right? And so that is one way to view quantum mechanics. I think it's perfectly legitimate. Now, it's untestable to prove or disprove that is actually the case. but it's one way, I think, of looking at quantum mechanics. And then you could say, well, what about splitting it? If time is going this way, right, and then space is on the other directions, what if you have a splitting that goes, the other way, right? I don't know. I don't know what the interpretation of that is, but maybe that's when you're looking at a particle and you see a superposition of states, right? And it's acting like it's both spin up and spin down. Maybe it's because it is both spin up and spin down, right? So that's, and then, so I think there's definitely potential ways to play around this and try to match up observations with theory, right? And so I think I can't quite tell you how to do it, nor can anyone else, and maybe at the end of the day it's complete nonsense. Okay? But it's not, I can't prove to you it's complete nonsense, and it definitely needs to be explored more, I would say. So you guys are the next generation of young thinkers. So what I would do is I would go back to every assumption that people are making, right? And not just say, oh, just for mathematicians, because I'm a physicist, I don't need to know what a topological space is. I don't need to know what Hausdorff and second countable are. No. Those might be invalid assumptions. Maybe that's not the right way to define a manifold, right? And maybe if you can adjust and come up with a more natural definition of manifold, then see what you get mathematically and try to connect it with some sort of observations, right? Does that give a better model of the universe? Does it, and especially if it allows you to make a prediction, allows you to understand. Because right now, it's worth noting out that we haven't figured out, I say we, humankind has not figured out how to unify general relativity with quantum mechanics, right? So, or this, quantum theory and the standard model of particle physics, right? So there's sort of there's two different realms of physics. And so, theory of everything is considered to be the biggest open problem. And how does one do that? I mean, string theory is the most famous example of an attempt to try to do that, but it's become pretty unfashionable right now. Right now, people are kind of mocking string theorists a bit. Like, you said you got this solved, and apparently you don't. Y'all are a bunch of scam artists, right? Y'all are a bunch of you're BSing us. Right, it's an awkward time to be a string theorist, actually, right? And they deserve a little bit of this, to be perfectly honest. Right now, they don't deserve. Now, here's the problem: they don't deserve too much because you've got to keep these things in balance, right? Because the point is, how about this? Give them enough mockery that they stop saying these are the only ideas we're studying. When they universally agree that we need to explore other ideas as well, then you can stop at that point. Because I think that's the real point, is we want to consider all the different ideas. So I hope you guys do that. Because we don't really know how these theories are going to unify. And string theory is almost certainly, it's definitely interesting mathematics. And I'd like to think that practically all interesting mathematics has something to do with physics. So I would think it would have some relevance. But we need to study everything. I'll just end on this and say, I think string theory is an example of groupthink. And I find it annoying. Actually, I find it really annoying that we all know groupthink happens up with regular people, right? Of course, they just form herds and like they just sort of think what they're told, right? We all get that, right? Like we see that with regular people, right? I mean, but it's just a bit disappointing when you see academics doing it too, right? And what we really celebrate is when we see people who aren't doing that, right? And really thinking for yourself, trying new ideas, exploring new ideas. And and that's something that we should value in academia. Because you have to come up with 100 bad ideas to get one good idea. Just don't ever forget that. And maybe this is a bad idea. Could be. Is the universe Hausdorff? Is it second countable? These are good questions. I can tell you one other thing, by the way. One other thing. And we discussed it already. I'll go ahead and share. And that is, there's another little technical detail we haven't discussed about the universe. Is that you say, the universe is a space-time manifold, right? Well, what is a manifold? Well, getting back to the more of the metrics, a little bit halfway towards the metric side of it, it's a bunch of overlapping coordinate charts, right? So you say, what's a two-dimensional sphere abstractly? Well, it's a map of North America and a map of Europe and a map of each continent and all the oceans, and they overlap in a certain way, and then you see the connectivity and you get a sphere, right? Okay. And the question is there more than one way to do that? Is there more than one way to have a bunch of overlapping spheres? I mean, overlapping coordinate charts so as to get a sphere? And of course there are. There's many different ways to do it. But they kind of all essentially give the same answer, right? So you'd say, okay, this is just like a mathematician's technicality, it seems like, right? But let me just point out that if you have a sphere, right? And again, this sphere is not sitting in R3, right? This is an abstract sphere, not in R3 necessarily, right? And so what you have is you have your UV coordinate chart over here, right? And that maps to some rectangle here, and then you have another UV coordinate chart over here, and that maps to some rectangle in the sphere over here. But then there's this overlap region, right? This overlap region, right? And now notice that if we look at this if we look at the coordinate chart mapping, which went here and then here, right? If we map from here to here and then go inverse map to here, we actually get a mapping from here to there, right? And so this is a coordinate, I'll call it C for coordinate chart mapping to another coordinate chart, right? So we get mapping, this thing is mapping a subset of R2 into a subset of R2. Fair enough? Not the whole space, it's subsets, right? Mm-hmm. And it's 1 to 1 on 2. And actually, let's require that this mapping be smooth. Right? It should be C infinity. In other words, it should be differentiable and so forth. Just a mapping from R2 to R2. That's calculus, right? Multivariable calculus. We want these mappings to be smooth. And if you have a bunch of coordinate charts and they're overlapping each other such that they are, all these composite mappings where they overlap are smooth, then we call that a smooth structure. Okay? So this is the notion of a smooth structure. In fact, a smooth structure then is the collection of, once you define a bunch of, let's say you have 7 mappings that cover the sphere, and they all are smooth with respect to one another on their overlaps, right? Then that defines a smooth structure, and then you can look at all coordinate charts that are smooth with respect to those coordinate charts, right? You can add them all in there and maybe put them all in there and call that a smooth structure. Okay, now the question becomes, how many smooth structures are there on a 2-sphere? And the answer is infinitely many. But it's for a stupid reason, because I could just take any smooth structure, right? And then I could sort of do some mapping where I reassign the points in a very unsmooth way with respect to that smooth structure, and then compose all the coordinate charts with that mapping, and I could get something that would look unsmooth compared to the others, right? And so then what we really want to say is, okay, but that's really kind of cheating. That's still the same smooth structure on a 2-sphere. I've just sort of renamed the points, right? And so up to that stupid idea, right, there's only one smooth structure on S2. And at that point, the physicists are like, okay, good. I knew I didn't have to think about this. Right? That's what we're all thinking. Okay, there's only one smooth structure on S2, so why are you wasting my time with this? Like, you're just told me something I already knew. Right? I'll tell you why. Because guess how many smooth structures are on S3? Just one. Okay. How many smooth structures are there on a donut, surface of a donut torus, 2-dimensional torus? Oh, just one. How about all surfaces? Just one. How about all 3 manifolds? Just one. Oh, okay. Well, this sounds like a big waste of time. A bunch of mathematicians getting paid for doing a bunch of stuff, boring stuff that no one really cares about. Shoot me, right? Like I don't want to play anymore. You're killing me here. You're wasting my time. Right? Okay, so I need a result here to get your attention. So here's the one that gets your attention. You ready? How many smooth structures are there on S7? You ready for it? 28. There are 28 distinct smooth structures on S7. It's understood extremely well. It was discovered by the mathematician and certified genius John Milner. Storied career. And so he's the first one to realize that there's something to study here. Okay, there's something to study here. There are 28 smooth structures on S7. First, to be perfectly honest, I don't really understand what that means. I mean, I sort of theoretically do, but it's saying that there's like, you do these overlapping coordinate charts, on S7, and there's 28 different ways, and in no stupid sense are they similar. They're genuinely different, right? Okay. How many smooth structures are there on S6? Anyone want to guess? I'll tell you. 1. How about S5? 1. How about S4? You ready?
1.
Nobody knows. Nobody knows. Open problem. You want to become world famous? Solve the question of how many smooth structures are there on S4. You'll be world famous. Okay? And that's kind of relevant because we live in a four-dimensional space-time. Okay, how many smooth structures are there on the real numbers? 1. How about R2? 1. How about R3? 1. How about R4? Infinitely many. How about R5? 1. How about R6? I think it's 1. It's some weird, this is very, very weird, right? So R4 is in terms of Euclidean space, you look at Rn, it's the first time you get more than one smooth structure, and they're infinitely many. But isn't the space-time supposed to be on R4, topologically? Yeah, it is, right? Okay, so which smooth structure are we supposed to use? Well, I have an idea. Why don't we just use the standard one, the one that we're all familiar with from molecular calculus, and never talk about this again? Right, that's where we are right now. Okay, this is the state of affairs. Like we were like just pretending like these smooth structures don't exist.
Is there some like underlying number theory reason why 4 is special, or is it like do you have any shallow?
4 is special in terms of topology. I mean, just the smooth structure thing is already quite striking, right? It's possible. You guys ready for this? Now I'm going to throw something on. This is not my idea. I did come up with this idea independently. But I think it's very similar to an idea some physicists came up with in the 70s. There's even a book out there. Do you remember the name of the book? What's it called?
Like exotic smoothness in physics.
Yeah, something like that. Physics and exotic smoothness, or exotic smoothness in physics, something like that. And so Google it. It's a PDF of the book's online. And basically the idea is maybe particles, maybe what we think of as particles is the exotic smooth structure. You know, maybe because like particles are these, they seem like they're not smooth, right? They seem like singularities, and so maybe you know when we're projecting, you know, with our little, you know, tiny brains, right, and we're trying to understand what's going on, and we're like, okay, well R4, I know what R4 is. It's this, you know, X, Y, Z, T, right? Okay, and then when we see a particle, what we're not understanding is we're using the wrong smooth structure, at least locally. There's like a concentration of, we got the wrong smooth structure, and so it seems unsmooth to us. It seems like a singularity. Do particle, because like from a general relativity standpoint, we really have no idea what a particle is. You know, we write down the stress energy tensor as if it's clear what that means or whatever, right? G equal 8 pi t, right? But what is that t? It comes from the particles, right? Somehow? Okay, but how does that work exactly? So, I don't want you to, the reason, why am I telling you this? I could, see, it's sort of like, do I tell you the truth or not? It's sort of like the Matrix movie. Do you want the red pill or the blue pill? Is that the two choices? Right? Do you want the blue pill or you want the, I think it's wrong for you to leave a class like this or to leave Duke and think that all the problems are figured out. There's nothing else to do, right? And here, I'm just going to tell you what to think. Here, think this, right? So what's the opposite of that? Is to tell you what we don't know, right? And what we don't know is what are all the smooth structures on S4 unknown. How about S3 cross S1? Because that'd be kind of relevant, right? Because, you know, we have universe is like R3 cross time, right? Yep. And so R3 at a point at infinity, right? That's S3. So S3 cross R. I asked my topology friends. This is called algebraic topology or standard topology course. This is called differential topology. Right? And so I asked my differential topology friends, hey, what are all the smooth structures on S3 cross R? And the answer is, nobody knows. Like, that'd be a good one to know. So, in other words, you would like to, if you wanted to come up with it, like, I would use the smooth structures on S3 cross R to probably come up with smooth structures representing particles, right? If perchance the smooth structure on S3 cross R, if the answer is not 1, if it's more than 1, and the number of smooth structures has anything to do with like the standard model of particle physics, oh my God, right? We got to really get to the bottom of this, okay? Like, is there a connection there, right? And probably not. But remember, you have to have 100 bad ideas to get one good idea. We don't know enough differential topology. That much is obvious. Like they're basic questions that us mathematical physicists can ask that would seem relevant to physics and we don't even know the answer, right? So there's plenty of math to still be figured out. And I think it's important, you guys are mathematicians and physicists. What's the smooth structure of the universe? Nobody knows. Is it Hausdorff? I don't think anybody knows. Is it second countable? Nobody knows. Are these even the right ways to model the universe? Right? Nobody knows. All right, you guys. All right, we'll see you all on Wednesday. We'll do our last review. Bring your test questions that you might have questions with, and we'll talk about it.